Hello, Chem 1110 students. We're up to the third video for chapter 1, and it is going to be about the metric system and density. All right, so first off, we're going to talk about scientific measurement, and these are called quantitative properties that can be measured. You don't use your senses to determine them. Any measurement needs to have units. We're going to talk about systems of units. Generally, we use the English system, which includes things like a foot or a gallon, a quart, which have very difficult conversions. Instead, in science, we use the metric system, which is based on some standards like the meter and liter, and all of the conversions can be done with base 10 exponents. So it's a nice simple system. It's actually called the International System of Units because it's used throughout the world. And there are 7 basic SI units that are listed here. Hopefully you're familiar with meters, certainly seconds. Temperature we're going to use quite a bit in terms of the Kelvin temperature scale, which we'll discuss. And then the amount of a substance, we typically in chemistry use mole, which we will also talk about in greater detail. Because there are only 7 units and they're of a particular size, we tend to use prefixes to be able to get either larger units or smaller units. A good example is computer memory. I can remember back when a kilobyte was considered big. Then we went to megabytes, and it was a big deal a few years back if you got memory that was in the gigabyte range. And now, of course, you can buy computers with terabyte memory. In the field of chemistry and medicine, we tend to use things like kilo. A kilo is what refers to 1,000 times. So a kilogram is how your body weight is determined. Volumes in medicine are often deciliters, so that's a tenth of a liter, and that exponent is 10 to the minus 1. In lengths, we talk about centimeters, so that's a hundredth with an exponent of minus 2. A milli, like a milligram, is 10 to the minus 3. And then we get into much smaller units like micro, nano, and pico. These are actually used all the time in the pharmaceutical industry because how drugs reside in your bloodstream tend to be at those very low levels. We used to work in terms of picograms, so 10 to the minus 12 grams, in a mil of your blood. That's like a needle in a haystack. Okay, mass is a particularly important unit. It is a measure of how much matter is in something. Typically, when you talk about how much matter is in your body, you think in terms of weight. But weight, which is the unit for which is pounds, is something that varies by gravity. And so we don't want that in science. We want to know absolutely how much matter there is. And so we use mass because mass doesn't change with gravity. The SI base unit for mass is a kilogram. And in chemistry, we're generally dealing with smaller amounts, so we use the gram. And the difference there is a factor of 1,000, remember. So a kilogram is 1,000 grams. Another unit that we use, which is derived from that basic SI unit, is a very small unit. It's called the atomic mass unit, and of course it's used to talk about how much mass is in an atom. And you can see an atomic mass unit is a very, very small portion of a gram, 10 to the minus 24th. The other thing that we deal with a lot in terms of quantitative properties are temperature. And the two that we tend to use in chemistry are the Celsius scale, which is a metric scale. So freezing point is 0 degrees for water, and the boiling point is 100 degrees for water. The Kelvin scale is an important scale when you're talking about fundamental properties, because 0 on the Kelvin scale is the lowest temperature out there. It's not been achieved yet, which is a good thing, because at 0 Kelvin, everything would quit moving and all matter would implode, which would be an issue for us. However, there is a conversion from Kelvin to Celsius, which has been determined mathematically. And so if you want to know the Kelvin temperature, you take that Celsius temperature and you add 273.15. Here we have a graphic that has a comparison of these three temperature scales. And so if you're looking at the boiling of water on the Celsius, we know that's 100 degrees C. And we add 273.15 to get the Kelvin temperature. And so a boiling water is at 373.15 Kelvin. On the Fahrenheit scale, though, it's 212, which is a very awkward number. Nonetheless, we use a Fahrenheit scale a lot in the United States, and these are the two important points: the freezing point of water, and that's at 32 degrees F, and we all use that number. If you have to drive somewhere and you're wondering if the rain that fell last night is frozen on the roads, you look at the temperature to see if it's above or below 32. Whereas the boiling point of water is 212 Fahrenheit, and I know a lot of people aren't even aware of that. So we quite often have to convert between Fahrenheit and Celsius in the United States. And so we use the fact that there are 180 degrees on the Fahrenheit scale between freezing and boiling, and only 100 on the Celsius temperature scale. So there's 180 degrees on the Fahrenheit versus 100 on the Celsius, meaning that the Fahrenheit scale, or the Fahrenheit degree, is smaller than a Celsius degree. And I got that 5/9 by comparing the 180 to 100. So we have a conversion equation, which is down below. Temperature in Fahrenheit, you would take the temperature in Celsius and multiply it by 9/5 and add 32 for that offset between the freezing point Fahrenheit being 32 and the freezing point Celsius being 0. So I have an example here. Body temperature of 39 Celsius constitutes a high fever. Convert this to a Fahrenheit scale. And this actually is a very important and typical conversion to do. We have a daughter that moved to Germany. She lives in Germany now, and she was always having to convert the temperatures to Fahrenheit because that was her reference point. So to do this, we use that equation I had on the previous page, except for we're going to substitute where it says temperature in degrees C. We're going to substitute our 39 degrees, and we have to both convert for the size of the degree, and we have to add that offset of 32 degrees F. And the temperature comes out to be 102 degrees F. So 39 Celsius is 102 degrees Fahrenheit, which we know would be a fever. So there's just a question here, are the Fahrenheit and Celsius temperatures ever the same? And it is possible that they have this same number value at the same temperature, which happens to occur in places like Minnesota. In fact, I had a professor who said when the temperature was such that it was the same number on both the Celsius and the Fahrenheit scales, he moved out of Minnesota. So what we're going to do is say, well, if the Fahrenheit temperature is minus 40 degrees, what is the temperature on the Celsius scale? And so we use our formula from the previous page, and we see that when the Fahrenheit is minus 40 degrees F, the temperature on the Celsius scale is also minus 40 degrees, in this case C. So indeed, that is very cold. All right, we're going to talk about derived units. One is volume and one is density. So there is not a volume unit on the SI scale. But as we know, you can get the volume of a cube by multiplying the length times the mass times the width. And so in this case, that derived unit, if you take that volume or cube of that volume, that would be a decimeter cubed, which is a liter. And 1,000th of that would be a milliliter, because milli means 1,000th, and that happens to be a cubic centimeter. And so that's why quite often in medicine, instead of talking about mils, they'll talk about cc's, which stands for cubic centimeter. Another derived unit is density, and density is very important property of a material because that's an intensive property. So it defines it, and it does not vary by how much of the material you have. So it's the ratio of the mass to the volume. And I have the definitions here for our abbreviations. And generally, so the SI derived unit would be a kilogram per cubic meter, using those standard units. But generally, we use slightly different units based on that state of matter that we're talking about. For solids, we usually use grams per cubic centimeters. Liquids would be grams per mil, and gases would be grams per liter because they have much larger volumes. All right, that is the end of our third PowerPoint.